Hey, welcome to topic 3. We're doing lesson 1. We're going to learn about some things, but you know what? A lot of this is review. And I tell you what, this isn't going to be a 28-minute video. I don't know what's up with that. We're going to learn how to convert exponential equations into logarithmic. I feel like we already know how to do that. And we're going to go backwards. So I feel like we still know how to do that. And then lastly, we're going to learn how to solve some of these. We'll learn some tricks in our calculator. We're going to start on page 629. Here is some review we're going to start with down at the bottom. The key here, it says solve for each unknown. Now, we know that this whole section is about logarithms, so the most important part of the logarithm is the base. Just ask Megan Trainor about that. Get it? So this one is 10 to the x power. Is there any way to write this with a common base, the same base? Now, how do we read this decimal? A lot of you would say 0.1, but actually it's technically 1/10, right? So that's the same as 1 over 10. And we know that 1 over 10 is the same as 10 to the negative 1 power. Now, a lot of us actually didn't know that because, for whatever reason, we never got that. But 10 to the negative 1 power means 1 over 10 to the first power. So we now need to start remembering these rules. Negative exponents mean you put the base in the bottom, and you make it positive. So 10 to the negative 2 would be 1 over 10 squared. Okay, that's the rule for negative exponents. Why did I flip my page? I'm not done yet. So anyways, back to number 1. If we see a number like 1 over 10, I've got to get the bases the same. I need a common base, 10 here. So this is 10 to the x equals 10 to the negative 1. Guess what? These exponents have to be the same because the bases are the same. So we're going to get x equals negative 1. Boom, for that one. Number 2, in that same idea, can we rewrite 16? 16 is 2, 4, 8, 16. It's 4 2's. So 2 to the x is going to equal 2 to the 4th. And that means that x has to equal 4. How about number 3 here? This is an identity exponent. What exponent will make you equal yourself? And that would have to be very simple. It has to be 1. Okay, so 1084 to the first power will equal 1084. And then our last property here, how do you get the whole expression to equal 1? Well, that means that the exponent has to equal what? 0. Anything to the 0 power equals 1. Those are our answers, and I feel good about them. So let's turn the page. We're on page 629. Just kidding. We're on page 630. It's a two-way street. We're going to talk about writing exponential form equations into logarithmic form. You've done a little bit of this, and I would tell you that the most important part is that base. Okay, whatever that base is has to be the base of the logarithm. So this is going to be log base, what's the base? 12. Okay, now it all equals the exponent. So it's going to equal that exponent. Logarithms are exponents. And that means the only other place for the 144 is right here. That's called the argument. So the base, the argument, and the exponent. Exponent always goes by itself. These are two different equations, but they tell you the same relationship. Okay, so we can go from an exponential form into our logarithmic form. And guess what? We can go the other way as well. As I said, the most important part is that base. That little number right there, we're going to put it right here, 16. And then a logarithm is equal to the exponent. The exponent is out here by itself. So this means that 16 to the half power equals 4. And if you remember what a half power means, that means the square root. So the square root of 16 is 4. That seems to work out. All right, let's go to the next one. 10 to the 5th equals 100,000. So log base 10. Now here's a little trick. I don't need to write the 10, but I can, but I don't need to write it. But the base here is 10. I know it all equals the exponent, so the exponent has to go over there. Now I'm going to write 100,000. Why don't I have to write that 10? If you don't write the 10, then we're assuming that there's a 10 there. That's just called a common log, as opposed to a natural log. What happens if you have ln, the natural log? Well, that means that we have a log base e. Remember e? That is Euler's number. All right. This is equal to approximately 3. If I were to write that in exponential form, remember, the most important part is that base. So I start with that base. It would be e raised to the exponent, which is third power, would be, in this case, approximately equal to 20.086. Why don't we just pause the video right now and you can finish the rest of the table? You can do it. Pause the video, finish the rest of the table. Ready, set, go. Okay, welcome back. This is what I got. Pretty easy, right? I mean, just make sure that the base is the base. The base of the exponent is the base of the logarithm. The exponent has to go all by itself. And if you do that throughout the table, you're good to go. So now's probably a good time to actually learn what all of these different terms are. According to your book, now's a good time to do that. So, as we go back and forth, we talked about that base being the most important. And then the exponent always goes by itself. The other term is called the argument. Now, some of the things we need to learn. Okay, the base has to be greater than 0, but not equal to 1. Because if you have 1 to any power, always equals 1. So that doesn't really help us out here. So the base has to be greater than 0. So base has to be positive. The argument must be positive as well. It has to be greater than 0. No negatives for the base. So the base can't be negative. And then the argument can't be negative. And then the value of the exponent can be anything. Okay, and remember, if the exponent is negative, suppose we have a negative value. I'm just going to say 10, and we put a negative exponent. That doesn't mean that our result is negative. Our argument would be negative. Remember, that means it's 1 over 10 to the positive 4. So that negative can't be a negative on the base, can't be a negative on the argument, but it can be a negative exponent. The value of the exponent has no restrictions. It's important to become familiar with how the base, argument, and exponent fit into a logarithmic equation. All right, so now we just have some more practice. We're talking about practice? Talk about practice. You arrange the given terms to create a logarithmic equation. You basically have to look at the numbers and figure out, like, how are these related to each other? Start with A. A is pretty easy. We have a 49, a 2, and a 7. So, by looking at this, hopefully we can figure out that that means that 7 squared equals 49. They want us to write a logarithmic equation, so I would write the log of the base always equals the exponent. All right, and then so that means 49 goes right here. So that would be the logarithmic equation for part A. Part B, okay, so I noticed that I've done a couple of these, so I know that this is 6 to the third power, right? So how would I do all this? It'd have to be 6 to the third power. Third power is in the bottom though, so it'd be negative third power. So I think this would be the relationship right here, right? That's true. That is a true thing we need to wrap our head around. So to write it as a logarithm, I'd say log. It's all about that base. It all equals the exponent. And that means the 1 out of 216 would be the argument that goes right there. All right, why don't you pause the video and do C and D all by yourself. Pause the video and do C and D all by yourself. Because I'm all about that base. So here's what I got. The first couple, we wrote it in exponential form. That kind of helped us figure out the logarithmic form, but eventually you want to get to the point where you can just write it in logarithmic form. Okay, log base 4 of 4 equals 1. Log base 4 of 256 equals 4. Remember, the exponent always goes by itself, and the base is on the log. Easy enough. Now we're going to use these skills. We are on 632 now. We're going to use these skills to figure out how to solve these equations. Okay, your book has, they make it very systematic where if the argument is unknown, if the exponent is unknown. For all of these, I'm reading what they're doing here. That's great. But for all of these, what we're going to do is we're just going to rewrite it in exponential form and then see if we can figure it out using a common base, or maybe we can just evaluate 4 to the third power. So let's do some examples and kind of look at that. Ooh, we got a lot of examples here. It's going to make a 28-minute video. I want to avoid that. All right, first one. We have log base 8 of 64 equals n. If I just rewrite this, that means that 8 to the nth power has to equal 64. So if we can get a common base, make the bases the same. I know that 64 is 8 squared, right? So this is 8 to the second power. If the bases are the same, then the exponents have to be the same. So guess what? N has to equal 2 for 3a. Okay, how about for B here? If I rewrite this, we have n to the negative 2 power has to equal 1 over 16. Well, that negative 2 is going to give me a little hint here. So n to the negative 2 is going to equal, we're talking about something squared and then being put in the bottom. This is 1 over 4 squared, which means that on the right-hand side, we get 4 to the negative 2. Let me erase that out. Take care of business here. What am I doing? So this is 4 to the negative 2. So notice how n to the negative 2 is going to equal 4 to the negative 2. These bases have to be the same because the exponents are the same and each side is equal. So here n is going to equal 4. All right, let's look at part C here. This one's going to be, this is a little tricky here. What do we got? 1/2 raised to the nth power has to equal 64. You're like, Mr. Kelly, how am I supposed to do that? That's crazy. Well, when you look at this, all right, 2, 4, 8, 16, 32, 64. That's 2 to the 6th power. I know this is 2 to the 6th power, right? And I know that 1/2 is 2 to the negative 1 power, right? So we get 2 to the negative 1 power. That's 1/2 raised to the n should equal 2 to the 6th power. The key here is to get a common base. And I know they're both, what do we get? We can write them as both with a base of 2. So using my exponent rules now, so 2 to the negative 1n has to equal 2 to the 6th. The bases are the same, right? So now I know the exponents have to be the same. So let's do that little equation. Negative 1n has to equal 6. And if I divide by negative 1, I'm going to get n equals negative 6. That is fun. That's a little tricky. I'm going to say that again because that's a little tricky, that one there. See, I know I can write this as a power of 2. That's 2 to the negative 1 raised to the n. And I know this is a power of 2. So if I write them both as powers of 2, I can use my exponent rules. When you have powers to higher powers, that means you multiply. And that'll give us negative 1n. Then I set them equal. That was fun. Let's try this one. Log of n equals negative 3. So if I were to rewrite this, I know that there's a missing 10 there, right? That's common log. So 10 to the negative 3 has to equal n. Well, I know that 10 to the negative 3, here's my exponent rules, means 1 over 10 to the positive 3. That's what that negative exponent means. That's a common theme in this lesson. So 1 over 10 to the third. 10 to the third power is 1,000. So that equals 1,000 for n. Let's go down to e. E gets a little tricky too. We're going to have to do a little trick for e. What do we see here? This is, I see the 3 and I see the 3, right? So they both have a 3. And there's a 2 here. Let me rewrite this as n to the 2/3 power has to equal cube root of 49. Ugh, that is ugly, right? But I know that 49, based off of my fancy math that I've learned before, I know that that is just 7 squared, right? That's just 7 squared. So that equals the cube root of 7 squared. And I also know that a cube root means raised to the 1/3 power. So n to the 2/3, I know has to equal 7 squared raised to the 1/3 power. This one takes a little more room here. Let's follow it up here. Okay, so n to the 2/3 equals 7 squared to the 1/3 power. This is ugly. Well, my exponent rules say I can multiply those. So n to the 2/3 power is going to equal 7. 2 times 1/3 is 2/3. Guess what? N has to equal 7 here. I'm going to talk through that one again. When I look at this, I notice that 49 is 7 squared, and I have an exponent of 2, so that might come in useful. I also know that I have a cube root, and a cube root means 1/3 power. So I'm going to rewrite the 49 as 7 squared, and then raise it to the 1/3 power, and that means this will equal 7 to the 2/3 power, which is basically we have n to the 2/3 power, so n must equal 7. Whew! Let me take a break from that one. We rewrite this one. 9 to some power has to equal 27. Well, you're like, Mr. Kelly, how do I do this? 9 squared is 81, so obviously it's less than 2. But you know what I can do? I can rewrite that 9 as 3 squared. So 3 squared to the nth power has to equal, and I can rewrite that 27 as 3 to the 3rd power. 3, 9, 27. So look, common base. That's the key to this whole page is a common base. How can I get these in a base that's common? On the left, we're going to get 3 to the exponent rules. 2 nth power is going to equal 3 to the 3rd. Guess what? If the base is the same, then I know the exponents have to be the same. So I'm going to rewrite that over here as 2n equals 3, and I can divide, and get n equals 3/2. So that's a little bit messy. We have to know our fraction rules. We have to know our exponent rules. But hey, ooh, box that. That's not too bad, right? It's not too bad if we get a common base. So you should be good. So now we're going to turn to page 633, and this is the part of the magic show you will all like. Write 3 logarithmic expressions that are equivalent to the given expression. So this means there are lots of possible answers. There are lots of possible answers. So part A here, 4A, log base 5 of 625. Well, let's just figure out what this is. Like 5 to what power? What does this all equal? Let me set it equal to x. So 5 to the x power has to equal 625. All right, so after we do a little bit of figuring out, we're going to know that x has to equal 4 here. So I just need to write 3 logarithmic expressions that equal 4, right? So in other words, I need 3 expressions where the exponent would be 4. So to help me out over here, I'm just going to do, you can pick whatever, but I'll do 2 to the 4th, and I'll do 3 to the 4th. I won't do 5, but maybe I'll do like 10 to the 4th. You can pick any numbers you want. And so 2 to the 4th, what does that equal? 2, 4, 8, 16. And then 3 to the 4th, that'll equal 81. And then 10 to the 4th will be 100 times 100. That's a lot of zeros. All right, so those are my expressions, right? I need to write 3 logarithmic expressions. These are exponential expressions. So the first one, I'll just write the first expression we have here. Log base 2 of 16 equals 4. That's one expression. Log base 3 of 81 equals 4. That's my second expression. Log base 10. I don't have to write the 10. Let's see. What am I doing? See, I just messed myself up. 10,000 equals 4. Those are my 3 expressions right here. I'll do one more for you, and then you'll do 2. I'll go down and I'll do D. So log base 2 of -2. What? That can't be negative. You can't get a negative here. Can't be done. Does not exist. We can't do that one. All right. That's what I did. You do the next 2. Pause the video. Do the next 2. Ready, go. Okay. How did you do here? The part B, the log base 7 of 1/7. That means the exponent here has to be -1, right? So you could write any logs that would give you an exponent of -1. Okay, so log base 2 of 1/2, log base 3 of 1/3, log base 1/4 of 4. That's a little trickier. Log base 4 of 1/4, log base 5 of 1/5. All of those work. Part C. This is all equal to 1/2, right? Because this is square root of 64 will equal 8. So if you notice, these are all square roots here. So the exponent on this one has to equal 1/2. So you can write any 3 for that. And then as we said, D is not possible because you can't have a negative there. Why would they ask you to do it if it's not possible? That is really sus. All right, 4, estimating. Here's the part that I thought we were doing earlier, but we're doing it right now. Let me pull that calculator out. We are going to pull out our calculator. You're going to love it. We're going to estimate these logarithms. Your book has a way to do it with a number line, but we're just going to use our technology because we need to know how to use this technology. Log base 2 of 10. Let's check it out. If you hit your your calculator, you hit the math button, and you scroll to the bottom of the list, there's this one called log base. Okay, so log base. So you can just type in the 2, you can type in the 10. So before I hit enter, let's approximate and see what we're supposed to get here. 2 to what power will equal 10? I know 2 to the second power is 4. 2 to the third power is 8. So it's a little bit more than 3, right? So we're going to estimate it, 3.32. We're going to want you to do that to the nearest 10th place. The 10th place is point that, whatever that is. So we have to look at the next number. If it's 5 or higher, we go up. We know how to round, right? So this one's going to be approximately equal to 3.3. All right, let's try the next one. The next one is log base 5 of 4. So it has to be less than 1, right? Because if we have 5 to the first power, then it equals 5. But this is only 4. So let's try that out. I hit math. Little shortcut. You don't have to scroll down if you scroll up. What? Now, full disclaimer. If your calculator does not have this, it might need to be updated. So bring it to a teacher so we can update it. This one will work out to, when you evaluate, 0.086. Now, it's 0.8. The next number is 6. So this is going to round up to 0.9. We are rounding to the nearest tenth. So this is 0.9. All right, you try the next two on page 637. Figure out these two right here. Pause the video, do those two by yourself. Go. Okay, so I get 4.1 and 3.4, and I add a little request here. Please don't come up in the middle of the master check and say, I didn't have a calculator, so I don't know how to do this. Make sure you learn how to do this before you take the mastery check, of course. If you're taking notes at home and you don't happen to have a calculator, that's fine, but just make sure you learn how to do it before you go in and take that mastery check. All right, last part, always, sometimes, never. I'm going to do 3 of these, but then the rest will be for your homework. Complete each sentence with always, sometimes, or never to make it true. The value of a logarithm is blank equal to the exponent of the corresponding exponential equation. Well, we know that logs are exponents, so this one's going to be always true. Easy enough. How about the argument of a logarithmic expression is blank, a negative number? Okay, the argument, can it ever be negative? If we do, remember the argument is this number right here. Log base b of a equals c. This number is the argument. Can that ever be negative? Never. Okay, and then lastly, the value of the logarithm, which is basically the exponent there, is blank negative number. Can the exponent be negative? Well, sometimes. Sometimes we can have a negative there. That's okay. Remember, the exponent can be anything, which is the value of the log. The value of the log is the exponent, right? All right, so you have the rest of them to do. Make sure you go through, and if you're not sure why it's always, sometimes, or never, make sure you ask your teacher. And that's basically it. Here are your practice problems. Is this 28 minutes? It's not 28 minutes, is it? All right, so it's a win for me. Remember, it's nice to be important. It's more important to be nice. Good luck.